This video will cover section 8.3, matrix operations and their applications. And just in case you are wondering why I'm not doing section 8.1, it's because I want to save that for class. It is a little bit more challenging than this one. And also I want to see your faces when you are suffering for doing that sorting, while you're doing that sorting by hand. But anyways, moving on. I know that you're not a big fan of matrices, but they're actually very important, and there are countless applications of them. And so all of you that, you love technology, you love your smartphone, or you love to read your email, also Netflix, you all love Netflix. So let's just take a minute to read this paragraph or a couple of paragraphs. So you use your smartphone to read your email, turn on your computer to write a paper. When you need to do research, you use the internet and browse through art and museums. I don't know if that's very true. And photo exhibits. When you need a break, load a flight simulator program and fly through a photorealistic computer world. Okay, I don't know if all of that applies to you, but I'm sure your smartphone does. As different as these experiences may be, they all share one thing. You're looking at images based on matrices. So I know I did talk to you about that, and today we will cover a little bit more of that. Matrices have applications in numerous fields, including the technology of digital photography, in which pictures are represented by numbers rather than film. So each pixel is actually a number. In this section, we turn our attention to matrix algebra and some of its applications. So before you start crying and complaining, just be grateful that you have matrices in your life. If you didn't have those, you couldn't have all of those electronic pictures that you have. So let's look at notations for matrices. And before anything, we're going to use capital letters to refer to matrices such as A, B, or C. Lowercase letters, they will imply, they will represent a specific entry inside the matrix. So for example, for matrix capital A, we could refer to each element by using a lowercase a, and here the letters I and J represent, each letter represents one thing. So I represents the row, and J represents the column. So let me give you an example. If we have something such as A32, not 32, 32, that means that that entry is located in the third row and second column. Another example, the entry, well, let's just do that one, since we're going to be working with those. So let's go to the next slide. Now, matrix notation. The order of a matrix, that refers to the dimensions of the matrix, and more specifically to how many rows and how many columns. So what is the order of matrix A? And remember, first we mentioned the rows. So here you can see 1 row, 2 rows. So we're going to say 2 by, we have 3 columns, 1, 2, and 3. So this is a 2 by 3 matrix. Now, second, well, part B. If matrix A is defined as every entry, lowercase a, with I being the row and J being the column, identify the entry A, 2, 3. And so for that one, we want second row and third column, so that will be second row, third column. So we're talking about this one here, so that's going to be negative 1/5. Now to answer the next question, A sub 1, 2, not 12, but 1, 2, that will be first row, second column, so that will be number 2. Now let's talk about the equality of matrices, and we're going to say that two matrices are equal if and only if they have the same order or the same dimensions. And also, and corresponding elements are equal. And of course, we have a more formal definition here. I do want you to pay attention to it. So we have the two matrices, let's call them A and B. They are equal if and only if they have the same order, which is the same thing we mentioned. So let's say the order, the dimensions of these two matrices are n times n, and they both have the same. And also, for every single element in matrix A is equal to every single element in matrix B that have the same corresponding row and column. So, for example here, and here, well, before we get to the example, let's look at the statement here. Remember, we say I represents the rows, and the rows, they start from row 1, row 2. We don't know how many in between, but we know that the last row is M. And how do I know that? Because of this. This tells me the total number of rows. Now, we look at J, that represents the columns. And we know that we start with the first column, second column. We don't know how many are in between, but we know the last one is N. And how do I know that? Because we have the dimensions of the matrices. Now, for those of you wanting to get in engineering, computer science, that is actually very important. And we call that a counter, where you count the elements. So element 1, 2, well, first row, second row. And you can have a counter that goes in both directions. Well, count the rows, count the columns. And so, please, be open-minded. This is actually not the hardest thing you'll see in your life, but if you don't learn this, how can you move on? So, moving on. Using the definition of the quality of matrices, we're going to compare the elements that have the same dimensions, where the I and J are the same. So, what that means is that X is in first row, first column, and so is 1. And so what we can say here is that X must be equal to 1. For matrices A and B to be equal, that will be if and only if every single entry with the same dimension, with the same address, same row and column are equal. Similarly, we could say that Y plus 1 has to be equal to 5. Y plus 1 equal to 5. Here we have 6 equal to 6. We don't need to do anything to that one. And let me just get a different color here. So we can also say that Z is equal to 3. So if we have that, then we know that matrices A and B are equal. So just to finish this problem, we have X is equal to 1. And here we will say that Y is equal to 5 minus 1, so Y is equal to 4. So remember, the if and only if, that is a double if statement. We could also represent it with a double arrow. So what that means is that if the elements are equal, then you could say the matrices are equal. Or if you start by saying the matrices are equal, that means that the elements are equal. Remember, double if statement. So moving on to the next slide. We have here the properties of addition and subtraction. And so for two matrices to be added or subtracted, they must have the same dimensions. So if we have a matrix that is a 2 by 2, it can only be added or subtracted to another matrix that is also a 2 by 2. If the dimensions are not equal, then the addition or subtraction is just simply undefined. So that's why here we have the statement saying they must have the same order. And what you will do is you will either add or subtract the elements that have the same address or that share the corresponding positions. So what that means is that the element on first row, first column will be added, in this case, to the element on the first row, first column. And so what we have here is a definition. Those of you going into computer science, you might have to deal with things like this. So what you will do is you add every element that has the same I, meaning row, and the same J, meaning column. And then, of course, if you're writing some type of code, you might have to have a counter there. So 1, 2, 3, and so on. Computer science, you might be doing things like this. You make I, and then I plus 1, and so on. All right, so let's go ahead and perform the addition and subtraction of the next two matrices. And just to make sure, let's check the dimensions. Here we have 2 rows, 3 columns, 2 rows, 3 columns. So they have the same dimensions. Of course, we can add them. And of course, you could do this in your head because this is a very elementary operation like what you used to do in kindergarten. But there, for your exam, your take-home exam, I need to see your work. And what I mean is I need to see what I'm about to write. In this case, I will add 0 plus -2, or I can just say -2 because they have the same location. Then I will add 5 plus 3. Then 3 plus 5. So I am done with the first row. Now let's move on to the second row. Now will be -2 plus 7. We have 6 minus 9. I am not subtracting, I'm just adding a negative number. -8 plus 6. So my resulting, I was going to say product, but what I get from adding those two matrices will be -2, 8, 11, 5, -3, and -2. Next one. Now I'm going to subtract, so I will have to, of course, distribute that negative sign. So I will write it this way. -6 plus 5. -6, negative times negative, that is positive. So that is why I have -6 plus 5. Next, 7 minus 6. Next, 2 minus 0. And lastly, -3 plus 4. Why is it plus 4? Because we have negative times a negative. So the difference between those two matrices will be -1, 1, 2, and 1. So moving on to the next slide. A zero matrix is a matrix whose elements are all equal to 0. So what we could say here, and we have the example here. This is the zero matrix. Every entry inside is equal to 0. And so if A is an n by n matrix, and B is a zero matrix, then A plus B is equal to A. So let's see if it's true. If we add -5 plus 0, of course, is -5. 2 plus 0 is still 2. 3 plus 0 is still 3. And 6 plus 0 is 6. So what we could say here is that the 0 matrix which in this case we're calling B, is the additive identity of matrix A. And please keep in mind that I'm using the word additive, not multiplicative. So what we could say is that if we add matrix A plus matrix B, but now I'm not going to call it B anymore. Well, actually, yes, I'm sorry. So if we add that to this matrix, we will get the 0 matrix, which we're calling matrix B, right? So what we could say is that matrix, this matrix here, -A, is the additive inverse of matrix A. And remember, I'm using the word additive. Now let's go over some properties of matrix addition. So we have matrices A, B, and C. Remember, matrices are denoted with capital letters. And we are going to assume that they all have the same dimensions, because that is the only way that we can add them or subtract them. We also have the 0 matrix, and that is also, it has the same dimensions as matrix A, B, and C. So we're going to define 4 properties. The first one is the commutative property of addition. Excellent question for your video. And so that will be that if we change the order, so if we add matrix A plus matrix B, it will be the same as adding matrix B plus matrix A. That is the commutative property of addition. Next question, associative property of addition. And so that, let's say we have matrix A plus matrix B, and they're both associated by this parentheses, they're together. And so we add those two, and then we add matrix C. So that will be the exact same thing as adding matrix B plus C, and then adding matrix A to it. So that will be the associative property of addition. The next one, we call it the additive identity property. And that will be the following. If we add any matrix to the 0 matrix, we will obtain the same matrix. And also, we could say that since matrix addition is commutative, we could write it the other way. So it will be matrix A plus the 0 matrix is equal to the 0 matrix plus matrix A, and that will equal to matrix A. That is the additive identity property. Remember, which one is the additive identity of matrices, and that would be the 0 matrix. Great question for your quiz. Next one, additive inverse property. And so that one tells me that if I add a matrix plus its additive inverse, which in this case will be -A, and let's not forget that addition of matrices is commutative, so I could also state it in this way, -A plus A, it will give me the 0 matrix. So if you use a matrix plus its additive inverse, you end up with the additive identity, which is 0. So that is how they are connected. Now, let's move on to the next thing, which is the definition of the scalar multiplication. Before we do that, let's remember that this number here is what we call a scalar, a number. And this one is pretty simple. All you have to do is distribute the number, right? So what I'm going to do is write it this way. I'm going to multiply 4 times 2, 4 times 5, 4 times negative 3, and 4 times 0. So in this case, the scalar multiplication of this matrix times 4 will be 8, 20, negative 12, and 0. So now let's look at the formal definition. And we have that if A is a matrix defined like that, of the order, the dimensions are m times n, and we have that C is a scalar. Remember, that is just a number, a constant. It could be positive, negative, it could be a fraction, it could be a decimal. Then the matrix CA, the product of that scalar times the matrix, it will have the same order as the first one, as the original matrix, the same dimensions. And what we will say is that every single entry of that matrix will be multiplied by the constant. And so we can define it this way. And this becomes very important to you, future computer scientists and engineers. So the matrix is obtained by multiplying each element of A by the real number C, just like I did on my example here. And so what we say about this matrix is we call it the scalar multiple of A. Excellent question for your quiz. So next slide. Now we're going to find the scalar multiplication. And also here we'll be doing some addition after scalar multiplication. So for the first one we have negative 5 times b. And I'm going to write it the long way. So it will be 5 times 2, 5 times negative 3, 5 times 5, and 5 times negative 6. So what will be the final answer? And that will be 10, negative 15, 25, and negative 30. And you might be wondering, do I have to do this? Well, for your test, which is a take-home exam, yes, you do. You have to do it if you want to get the full credit. Now, let's work on the next one, and we're going to multiply 2 times matrix A. So make sure you take the correct matrix. In this case, we will have 2 times negative 1, 2 times 4, 2 times 3, and 2 times 0. Now we're going to add the scalar multiple of matrix B times 3. So that will be 3 times 2, 3 times negative 3, 3 times 5, and 3 times negative 6. So the scalar multiple that comes from here will be negative 2, 8, 6, and 0. And to that, we're going to add 6, negative 9, 15, and negative 18. Now here, I'm almost out of room, so I'm just going to write down the answer. And that will be negative 2 plus 6, that will be 4. Then 8 minus 9, that is negative 1. 6 plus 15 is 21. And 0 plus negative 18 is negative 18. And so we're done with that scalar multiplication and addition. So let's go ahead and go over some of the properties of scalar multiplication. And we have here if A and B are matrices of that order, the dimensions are m by n. That means m number of rows, n number of columns. And we have the lowercase letters to signify scalars, numbers. So then the following properties are true. First, we have the associative property of scalar multiplication. And so that tells me that if we have two scalars, C and D, two numbers multiplying each other, and then multiply by a matrix, you can multiply the numbers first and then multiply those two numbers times the matrix. Or you could do the following. You can multiply one scalar times the matrix and then multiply that times the other scalar, and you should obtain the same product. We also have the scalar identity property, and so let's go back to real numbers and remember the multiplicative identity of any real numbers is 1. So 1 times matrix A is equal to the same matrix. So scalar identity property. Now the next property is the distributive property, and that tells me that you can have a scalar multiplying the addition of two matrices. And so we could add the two matrices first and then multiply them times the scalar, or we could also do this. We could distribute the scalar and say C times A and then plus C times B. So we will be multiplying the number times the matrices and then adding the resulting products. We also have another distributive property here, and that will be if we are adding two scalars, C plus D, adding two numbers, and then multiplying that times the matrix. And so we could add the two numbers first and then multiply, or we could get the product of C times A and C and D times A and then add them together. And so that is another example of distributive property of scalar multiplication. Now, what I'm going to do next is solve an equation, a matrix equation here. So that's why we have uppercase letters to solve for x. And so the equation is 2x plus a is equal to b. And what we know is that matrix A is here, and matrix B is here. So before I do anything with my matrices, I'm going to solve the equation just like if I was to solve a linear equation. So I have 2x is equal, and of course I'm trying to solve for x. So what I'm going to do is I have b on the right side, and I have positive a. So I take that across, it will do the inverse operation, and that will be subtraction. So it will be b minus a. Now the next thing to do is, we know that 2 is multiplying to x, so if I take that 2 and move it across, we know it will be dividing. So we will have x is equal to b minus a, everything divided by 2. However, with matrices, we do not have division, but we do have scalar multiplication, and I told you that your scalar could be any number, including a fraction. So we're going to say that x is equal to 1/2 times b minus a, because multiplying by 1/2 is the same as dividing by 2. So the way I'm going to find my answer is by doing the following operation. 1/2 times b minus a. And so what I want to do is I will like to subtract those 2 first and then find the answer by by multiplying them by 1/2. So first I will have 1, -5, 0, 2. Oh, I'm sorry, that is matrix A. I hope you're using a pencil. So matrix B goes first, that is -6, 5, 9, and 1. And then we subtract that. From that, we'll subtract matrix A, which is 1, -5, 0, and 2. So -6 minus 1, that will be -7. 5 minus -5, that is the same as saying 5 plus 5, it will be 10. Then we have 9 minus 0, so that is 9. And finally, we have 1 minus 2, so that will be -1. And to finish this, we have to distribute the 1/2 to every single entry inside of matrix. So 1/2 times -7, 1/2 times 10, 1/2 times 9, and 1/2 times -1. So that will be -7/2, 10/2, or 10/2, 9/2, and -1/2. If you can, you reduce. So the final answer will be matrix X is equal to -7/2, 5, because 10/2 is 5, 9/2, and -1/2. So let's move to the next slide. Now we're going to go over matrix multiplication of 2 by 2 matrices. 2 by 2s, remember we have 2 rows, 2 columns, 2 rows, 2 columns. And I don't know if you remember this from algebra 1, I'm sorry, algebra 2, but for you to be able to multiply 2 matrices, they have to have the same number. The number of columns of matrix A needs to match the number of rows of matrix B. And so I used to tell you if those two numbers in the middle are equal, then the product is possible. The resultant matrix is going to have the dimensions that you see here, 2 by 2. So that one, we're talking about 2 square matrices, so of course you can multiply them. So what we're going to do is we're going to multiply the first row times the first column, and that will go here. So A times B plus B times G. After that, we will multiply the first row times the second column, and so that will be A times F plus B times H. And that will go in the first row, second column. Remember, if we were to determine the location of this entry, that will be first row, first column. And this one is first row, second column. If you notice, we multiplied the first row of the first matrix times the second column of the second matrix. Now we move to the second row of the product, and we'll have second row, first column, so that will go here. That will be C times E plus D times G. And finally, we will get second row, second column, so it will be C times F plus D times H. Now let's solve example 5. So we're going to multiply A times B. just to make sure this is a 2 by 2, this is a 2 by 2, so of course we can multiply them. So first of all, I'm going to multiply the first row times the first column, and that will be 2 times 0 plus 3 times 5. Next, I'm going to multiply the first row times the second column, and of course add the products. So it will be 2 times 1 and 3 times 6, but we are adding them. Next, we take the second row, first column, so that will be 4 times 0 plus 7 times 5. And the last thing will be second row, second column. So 4 times 1 plus 7 times 6. We know that any number multiplied by 0 will be 0, so I don't really have to worry about those entries. So here I'm going to have 3 times 5 by itself, so it's 15. Here I will have 7 times 5, which is 35. And here I still need to consider both products. So 2 times 1 is 2, plus 3 times 6 is 18, so that gives me 20. Next one, 4 times 1 is 4, plus 7 times 6 is 42. So if we add those, I will get 44. Oh no, 46, I'm sorry. Okay, so that is matrix multiplication of a 2 by 2. If you did not understand, feel free to rewind the video. Not rewind, but go back. Okay, now for the product of two matrices to be defined, the number of columns of the first matrix must equal the number of rows of the second matrix. And that's where I was talking about positioning the matrices one next to the other and checking that the number of columns of the first matrix is equal to the number of rows of the second matrix. So those two entries must be equal. Now, after you check for that, then the resultant matrix, the product of those two matrices, after you multiply them, is going to be an M by, in this case, M by P matrix. So the dimensions will be M by P. So you take the numbers that are on the outside. So let's look at the formal definition. So the product of this matrix with the dimensions M by N times matrix B, which has the dimensions N by P, is equal, well, first of all, you check that the multiplication is possible. And so the resultant product will be that. So remember the numbers on the outside. And those will be the dimensions of matrix AB. And the elements are found as follows. the element in the ith row and jth column. Remember, we're using I to represent the number of rows and J to represent the number of columns. It is found by multiplying each element in the ith row of A by the corresponding element in the jth column of B, and also by adding the products. So when we say corresponding, we could use this example. Here, 1 is the first element of the first row. So that will be multiplied by the first element of the first column. Similarly, number 2 is the second element of the row, and they will be multiplied by the second element of the column. And lastly, 3 is the third element of the row, so it will be multiplied by the third element of the column. So that's what it means by corresponding. So when I and J are equal. So let's do a couple of simple multiplications, and remember that matrix multiplication is not commutative. So let's write that down. And this will be a very easy way to prove that it is not. So here we're going to be finding the product AB and then BA. And you will see we're now going to get the same thing. So matrix A, we will be using the matrices from here and here. Matrix A, let's write it down, and that matrix is the dimensions of that matrix. It will be 1 row by 3 columns. 1, 2, and 3. Matrix B, 4, 5, and 6. The dimensions for that matrix are 3 rows and 1 column. So remember, to make sure that the product is possible, you check the numbers that are here. Those two numbers happen to be equal, so yes, we can multiply them. But the dimensions of the resultant matrix are going to be a 1 by 1. That means that we're only going to have 1 row, 1 column. In other words, we're only going to have 1 entry, 1 number. So let's see what we're going to do. This will be 1 times 4 plus 2 times 5 plus 3 times 6. And remember, we need to add the elements that come from the same row and the same column. So that will be 4 plus 10 plus 18. And that will equal to 28 plus 4. So that is 32. And that is a 1 row by 1 column matrix. Now let's look at B times A. So now I need to write matrix B first. So that will be 4, 5, and 6. Matrix A is 1, 2, and 3. So the dimensions of matrix B are 3 rows, 1 column. And matrix A has 1 row, 3 columns. So just to verify, the number of columns matches the number of rows. We say those are equal, so we can multiply the two matrices, and the resultant matrix will be a 3 by 3. So now we're going to have 3 rows and 3 columns. And you might be thinking, how can we get that? So what's going to happen here is that we're not really adding, because we will be multiplying the row times the column. And there's not another element on this row that could be added to the product that it will have from another element for this column. So it will look like this. 4 times 1, that's it. We move on. Now we say 4 times this column. 4 times 2, and that's it. Now 4 times the third column. And we're done with the first row. Now we're going to move on to 5, the second row. So 5 times the first column. And then 5 times the second column. And then 5 times the third column. And we are done with those first 2 rows. Now let's go ahead and move on to the third row. So the third row here is 6. 6 times the first column. 6 times the second column. And then 6 times the third column. So the resultant matrix here is going to be 4, 8, 12, 5, 10, 15, 6, 12, and 18. And that is correct. So let's move on to the next slide. Now we're possible find each product. So let's start with the easy one, which is B. And I say that is the easy one because this product will be undefined. So let's see what. We have 2 rows and 4 columns. And here we have 2 rows and 2 columns. So if we check the 2 numbers here, they're not equal. So we're going to say that the product is undefined. We could say is not possible. Now let's see if we could perform the multiplication of part A. So we have a 2 by 2 and we have a 2 by 4. So in this case, yes, we can, because this number is equal to this number. And the resultant matrix is going to be a 2 by 4. 2 rows, 4 columns. First, we take the first row, and we multiply by the first column. So 4 times 1 plus 2 times 0. And we're done with the first column. Now we're still on the first row times second column. So that will be 4 times 2 plus 2 times 2. And it looks like I'm going to need more space. Then we're done with the second column, so now we move to the third column, still on the first row. So 4 times 3 plus 2 times -1. We're done with the third column. Now we move on to the fourth column. So that will be 4 times 4 plus 2 times 6. Now let's work the second row. So second row, first column, that will be 1 times 1 plus 3 times 0. So we're done with the first column. Let's move to the second column. And we'll have 1 times 2 plus 3 times 2. Next will be second row, third column. And the last one will be second row, fourth column. Now we have some numbers multiplied by 0, so here those will be 0. Now we have 4 times 1, that is 4. We have here 4 times 2, that is 8, plus 4, and then 12 minus 2, 16, plus 12. Second row, we have a 1, we have a 2 plus 6, we have a 3 minus 3, and we have a 4 plus 18. So we have 4, 1, 12, 8, 10, 0, 28, and 22. And that is correct. Okay, let's just go over some properties of matrix multiplication. Let's go over some properties of matrix multiplication. So again, we have matrix A, B, and C denoting matrices. And remember, we use uppercase letters. And we have C as a scalar, just a number, lowercase. And for these properties to be true, we're going to assume that the order, the dimensions of each matrix is such that all operations are defined. So we're not going to worry about looking at the checking for dimensions. We're just assuming that the products are defined. So we have the associative property of matrix multiplication, and that one states that if you have 3 matrices multiplying, you could multiply 2 at a time, 2 first, A, B, and then multiply it times the third one. Or you could do the following, multiply the second and third, and then multiply by the first, and you will get the exact same thing. Then we have the distributive properties of matrix multiplication. We're going to go over 2. So we could have a matrix multiplying the addition of 2 matrices, and that will be the same as if you multiply matrix A times B, and then you multiply matrix A times C, and then you add them. So you could either add the 2 matrices and then multiply them by A, or you could do the following. The second one, we could add 2 matrices and then multiply them by a third one. So first you add them and then you multiply. Or you could multiply the first matrix times C, then the second matrix times C, and then add them. And you will obtain the same product. The third one, the third property is the associative property of scalar multiplication. And that one states that if you have a scalar multiplying 2 matrices, you could multiply the 2 matrices first and then times the scalar. Or you can multiply the scalar times 1 matrix and then multiply that product times the second matrix. Now in this case, do not confuse it with this property, well actually this is not the same. C times A and then C times B. And why is that not equal? Because the scalar that you will be multiplying here by will actually be C squared. And so if you do that, you only distribute that scalar to 1 matrix and 1 matrix only, because you don't want to multiply by C twice. So let's go to the next slide. Now this is a very simple problem about pixels. And we know that from white to black, there are actually 256 pixels. And they go from 0 to 255, where white is 0 and 255 is black. And all the numbers in between are just shades of gray. Now for this book, we're only going to use numbers such as 0, 1, 2, and 3, where 0 represents white, 3 represents black, and 1 represents light gray, 2 represents dark gray. So we have a picture here, the letter L, I guess, and we can see the letter L is being formed by the pixels in dark gray. The rest of that square is being formed by pixels in light gray. So what we're going to do first is find a matrix that represents a digital photograph of this letter. So it is very simple. We have, for dark gray, we have 2. And for light gray, we have 1. So remember, I'm getting those numbers from here and here. So that is the matrix that represents the picture. Things are not as simple when you're working with those type of pixels. And if you get into color pictures, that's even worse. So now what we're going to do is increase the contrast of the letter L. So what that means is that you want to make your dark shades darker and your lighter shades lighter. That's how you increase the contrast of a picture. I'm sure you have done that maybe with Photoshop or any other software. So let's see what's happening behind the numbers. So like I said, we're going to change the dark gray to black. We're going to make it darker. And the light gray to white. That's how you increase the contrast. You make the two shades more distinct. So we have the matrix 2, 2, 2, 1, 1, 1, 2, 1. We're going to add a matrix. And what we want to end up with is we want darker shades of gray we want to turn those into black. And if you go back to the scale model or the conversion, we know that black is equal to 3. So we want those entries to be 3s. So what do we need to do to a 2 to turn it into a 3? And the answer is pretty obvious. You need to add a 1. Now let's look at the other pixels, the ones in light gray. So light gray is represented by 1. And we want those to turn into white. So the number that we're using to denote white pixels is 0 right here. So we want those entries to be zeros. So what do you need to do to a 1 to turn it into a 0? And the answer is pretty simple. You could subtract 1, or you could add -1. And let's just check. So 2 plus 1 is 3. 1 plus -1 is 0. 1 plus -1 is 0. And of course, the same applies for the second and third row. So that's very simple but very true application of matrices. So let's go to the next slide. Now the next and last 2 slides, they are going to relate to transformations of an image. And of course we have a very simple image here. It's a quadrilateral. And now what we're going to do is we're going to look at the columns. Remember how in Algebra 2 we used to look at matrices to represent equations. Every row was an equation. Now what we're going to do, and you might do this in physics, in engineering physics, or maybe if, let's see, if you take matrix algebra, any of you who is planning to become an engineer, you will need matrix algebra, which is the low-level class for linear algebra, and then some of you might even need linear algebra, which is the second level. So what we do here is that we look at the columns, and they also represent vectors. I think you have seen vectors in physics, so let's say that vector could be represented as -2, -3, something like that. We're going to do something like that in Precalc 2. But I know you work with those in physics as well. So with matrices, every column represents a vector. And so it tells you here the first row represents the x coordinates, the second row represents the y coordinates. So if we were to plot those points, remember the first row is the x. So we will obtain the figure that we have here. So just for practice, let's plot the points and then connect them. So we have -2, 3. So this first column, think of it as this, -2, -3. So it will be the point here. Then second column is -1, 2. Third column is 3, 4. And fourth column is 1, -2. So let's go ahead and connect them. And yes, we obtain the same shape that we have here. Now, what we're going to do is move the quadrilateral 4 units to the right and 1 unit down. 4 units right, 1 unit down. So what we're going to do is use the same matrix that contains the coordinates. -2, -3, -1, 2, 3, 4, 2. And remember, the top row represents the x coordinates. And so we want those x coordinates to move to the right, 4 units. So it makes sense that to every entry on the first row, we add, I'm going to say we add 4. 4 units to the right. Now we want to move move the shape 1 unit down. So we need to do some type of change to the y coordinates, which are second row. And so since we want to move that down, we will subtract 1 from every y coordinate. Or add -1. Same thing. So now the resultant matrix will be -2 plus 4, that is 2. -1 plus 4, 3. 3 plus 4, 7. 1 plus 4, 5. Second row will be -3 plus -1 is -4. 2 plus -1 is 1. 4 plus -1 is 3. -2 plus -1 is -3. So now let's go ahead and plot the points. So first column represents the first point. So it is 2, -4. Next column is the second point, 3 comma 1. Next column is the third point, 7 comma 3. I don't have enough room here, so let's make enough room. And then fourth column represents the fourth point, 5 comma negative 3. We connect them. And we have the image was translated 4 units to the right and 1 unit down. So some people actually work by doing things like that in animation, of course with more complex shapes, or also mathematicians who work with linear algebra, or physicists that work with vectors. Now, we're going to shrink the quadrilateral to half its perimeter. And I think you might be thinking what we're going to do, and we're going to multiply everything by the scalar 1/2. So the original matrix was -2, -3, that's the first point, -1, 2, 3, 4, 1, -2. And so remember, when we multiply by a scalar, we distribute that to every single entry. And we're going to take a little shortcut here. So we will say -2 over 2, -1 over 2, 3 over 2, and 1 over 2. Then we have -3 over 2, 2 over 2, 4 over 2, and -2 over 2. Now I'm going to simplify by dividing the numbers that are divisible by 2. So the first one, -2 divided by 2 is -1. And then we have -1/2, positive 3/2, positive 1/2, -3/2. 2 divided by 2 is equal to 1. 4 divided by 2 is equal to 2. And -2 divided by 2 is -1. Now I'm going to go ahead and plot the points. So remember, first column is my first point. So that is -1, -3/2, so that is here. -1/2, comma 1 here. 3/2, comma 2. And 1/2, comma 1. -1. Okay, and we're almost done. There's just one more problem. And now, before being told what kind of transformation they want us to do, we're going to do what it says here. So we have a matrix, and we're going to multiply that matrix, which is B, times matrix A, which is the original matrix that contains our original points. So the product of B times A is going to be -1, 0, 0, 1 times matrix A. And matrix A is -2, -1, 3, 1, -3, 2, 4, and -2. So remember, we need to multiply row times column. So we'll have here -1 times -2, and then we add 0 times -3. Then we move to the second column. So that will be -1 times -1 plus 0 times 2. And then third column, -1, -1 times 3, plus 0 times 4. And the last column, fourth column. So that is negative 1 times 1 plus 0 times negative 2. Okay, so that didn't work. Okay, now let's go to the second row. So it will be 0 times negative 2 plus 1 times 3. First column. Then we move to the second column, still on the second row. So we'll have 0 times negative 1 plus 1 times 2. Then we move to the third column, still second row. And that will be 0 times 3 plus 1 times 4. Then we have second row, fourth column, and that will be 0 times 1 plus 1 times negative 2. So we have here times 0, 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 and times 0. So we don't need to worry about those terms because any number multiplied by 0 is 0. So here, negative 1 times negative 2 is positive 2. 1 times 3 is positive 3. Negative 1 times negative 1 is positive 1. 1 times 2 is 2. Negative 1 times 3 is negative 3. 1 times 4 is 4. Negative 1 times 1 is negative 1. And 1 times negative 2 is negative 2. So now let's plot the points of that matrix here and on our grid, and let's see what kind of shape we get. So our first point is 2, 3. Second point is 1, 2. Third point is negative 3. Okay. I made a little mistake. And that is, I forgot to write a negative here. But that is easy to correct. Because I just need to look at the terms that were multiplied by the first column. So those are here. Here I actually have that negative 3. But here I don't. So this one needs to be a negative 3. That's it. That's all I need to correct, I think. Yes. Yeah, that was the other mistake. So let's go again. Let's plot the points. So 2, negative 3. That's here. And then we have 1, 2. Then we have negative 3, 4. Oh, I'm sorry. I'm not plotting the point right. Negative 3, 4. And negative 1, negative 2. That is here. So let's connect the points. And so, what type of transformation, what effect does that have on the quadrilateral? And we're going to say that it is a reflection across the y-axis. We can see clearly that the point here has an x-coordinate of 1, and the point here has an x-coordinate of -1. Similarly, with this is a 3, and this one is a -3. So all the x values were changed to the opposite value, which makes a reflection across the y-axis. And so that was done because of this one. We did not change the y values. The y values remain the same. So if you notice, when we were multiplying times the first row, all those y values were canceled out because they were multiplied by 0. Now, since we wanted we didn't want to change those y values, here we had a 0. Again, so those values were canceled. And so we also wanted to keep our y values the same. I'm sorry, the 0 made those x values cancel out so that we wouldn't change it again. So this 1 is what kept the y values being equal. And so that is what caused the reflection across the y-axis. This -1 and this +1. The -1 reflected the x values. The +1 kept the same y values. And so this is the end of the video. Make sure you complete your homework on Pearson. If you are in second period, it is due on Monday. As usual, if you're in seventh period, it is due on Tuesday. Also, you have a quiz on Edmodo. I have not created the quiz yet, but I will pretty soon. So have a nice weekend.